Okay, so now let's take a look at some other oxygen nucleophiles. Specifically, we're going to look at the formation of a functional group called an acetal from an aldehyde. These are also called ketals when they're formed from ketones. The way I make one of these is I take a compound like benzaldehyde and I treat it with an alcohol in the presence of an acid catalyst. Now here the alcohol is acting as both nucleophile and solvent, so we have a large excess of it. When the reaction is done, I'm going to get this diether here, sort of equivalent to what the hydrate looked like, and water as a side product. So this functional group is what we call the acetal. This reaction is actually an equilibrium process. It's sometimes hard to get it to go to completion. So the way we can do this is by using Le Chatelier's principle. There's several pieces of equipment or substances that we can use to remove water continuously as it's formed to force this reaction to the right. One substance we can use is a drying agent like molecular sieves or calcium sulfate. The other way that we can do this is with a piece of equipment known as a Dean-Stark trap. So I'd encourage you to look that up because it's a pretty cool piece of equipment and it's a very nice way of sort of manipulating the environment of a reaction to get it to do what we want. A bit of nomenclature here. How we would name this is we'd name this benzaldehyde diethyl acetal. So the way these are named is by taking the name of the parent aldehyde or ketone, the alcohol that we've added, and then tacking on acetal at the end. We'll see many different acids used for catalysis here. In addition to writing sort of the generic H+, you'll also see an old favorite, sulfuric acid. Sulfuric acid is water soluble, so it's very good for reactions where we're using things like ethanol or methanol alcohols. If we need one that's a little more soluble in organic solvents, we might use para-toluene sulfonic acid. Hey, we know how to make that. So toluene sulfonic acid is often abbreviated as TSOH, and it is soluble in a wide variety of organic solvents. So when we're going through this reaction, let's take a look at the mechanism of this, and then let's also say why we care about it. So who cares about these things? Okay, so the mechanism for this process is acid catalyzed, and it's known to proceed in sort of two general stages. In the first stage, we're going to treat our carbonyl group with our alcohol in the presence of an acid, and we're going to get a compound here that looks a lot like the hydrate that we formed previously. This is called a hemiacetal, and these compounds are usually unstable, though we'll talk about some exceptions to that later on. In the same conditions, in the presence of an alcohol with a catalytic acid, we lose water as a leaving group and substitute the second alcohol group in there. So, I want you to practice this, so knowing generally what we know about these mechanisms, propose a mechanism for the formation of the hemiacetal from ethanol and a proton in the presence of our aldehyde, and then finish the mechanism, show me how we get from the hemiacetal to what's known as the full acetal, our final product. Pause the video here, take a moment to do the mechanism, then we'll go over it together. All right, so hopefully we've predicted that the first step of this has to be protonation of the carbonyl group to create an oxonium ion, which is a much better electrophile and much better leaving group. Ethanol, a weak nucleophile, can now add to the carbonyl carbon to generate an oxonium ion, which will lose a proton to generate the hemiacetal and regenerate our acid catalyst. This part of the mechanism is directly analogous to the formation of a hydrate. What happens next is the OH group will pick up that proton, making it a much better leaving group. Water can now leave, assisted by the fact that we have lone pairs adjacent to water of our ethyl ether. This will make something that looks a lot like our oxonium ion. Now at this point, we can't just lose that ethyl group. It will not behave like a proton, but we have made it a very, very strong electrophile, so it can pick up another equivalent of our alcohol. This will give us another oxonium ion, which can lose a proton to form our final product, the full acetal. Right? And acid is catalytic in this process. It is regenerated in this last step. Nice. Okay, so an especially stable variant of this functional group is a cyclic acetal. A cyclic acetal can be formed from an aldehyde or a ketone when we treat it with ethylene glycol or some other diol. So here, instead of having two separate equivalents of an OH group that add to our carbonyl carbon, the OH groups are bound together by some sort of tether. And so we're going to get this cyclic formation like this, which is very, very stable. So these compounds are much easier to form, and they're actually also quite a bit more stable. So this is a really good place to practice your mechanism. So draw a complete arrow-pushing mechanism for the formation of this cyclic acetal, starting from the starting materials that we have above. Pause the video, come back to it when you're finished. All right, so instead of going over this mechanism here, what I want you to do is double check your work. So check it against the mechanism of acyclic acetal formation that we just showed previously. Your steps should all line up. If you're careful, you should be able to look through it and find an intramolecular substitution reaction that explains why these compounds are very stable. So let's go to the last part of the questions that we've been trying to answer, which is what are these things good for anyway? So let's say I propose this reaction. Take a moment here and look at this, and I want you to tell me what's wrong with the reaction that I've drawn. Right, we can't do this. So the aldehyde is the better electrophile. The better electrophile will always react with nucleophiles more rapidly. So to solve this problem, what I'm going to do is I'm going to do a reaction here. I'm going to add ethylene glycol and toluene sulfonic acid, and I'm going to make an acetal. Now the reason why I want to do this is because the aldehyde is going to react much, much faster than the ketone, so I can selectively form the acetal of the aldehyde. Now once I've done this, this acetal is essentially sort of a strange-looking ether, and much like ethers, this compound is going to be immune to reactions with strong nucleophiles or bases. So now what I can do is I can add my Grignard reagent followed by water for workup. This will add to my carbonyl group very cleanly, giving me this benzylic alcohol. And then if I add a proton and excess water, I use Le Chatelier's principle to force this back to the carbonyl group. So this is frequently referred to as a protecting group strategy. The acetal can be used to protect ketones and aldehydes from reaction with nucleophiles. Now the nucleophiles that we might want to see this with are ones that would react with both ketones or aldehydes, so things like organometallic reagents, lithium aluminum hydride, sodium borohydride, acetylide ions, any other strong nucleophile like that. So if you want some more good mechanistic practice at this point, give me a full, complete mechanism for the hydrolysis of an acetal. All right, so here's some synthetic practice. So I want you to draw the product of each of these reactions below. Go ahead and take a few minutes to do this. Pause the video, come back when you're done, and we'll check your work. Okay, for the first reaction, we get a dimethoxyacetal, so only the ketone will react. This type of reaction does not occur with esters. For the second reaction, we're making a cyclic acetal out of the diol, which you can see over on the right. For the third reaction, we're actually starting with the diol and adding an aldehyde. We would get this bicyclic intermediate that you see on the bottom right. Let's do some more practice. So let's propose some syntheses using an acetal as a protecting group. So each of these syntheses will only work if we can use the acetal to protect. Here's the first one, where we're trying to elongate the alkyne chain. This comes from, I believe it was chapter 9 in the Klein book. This one here, we're trying to reduce that ester using a reducing agent. So take a moment, pause this, work these through, come back, we'll check our work together. Okay, first synthesis. Step 1, make an acetal, protect that carbonyl group. Step 2, deprotonate the alkyne with a strong base, alkylate it with an alkyl halide, and then finally add an acid to deprotect and regenerate the ketone. Second synthesis looks very similar. We need to protect the ketone with a cyclic acetal, because when we add the reducing agent, the ketone would react much faster than the ester. Now in this reaction, if we add H3O+ to work up the alkoxide that we get out of the reduction step, this workup condition will also be sufficient to deprotect our protecting group. So one thing that you have to be careful about with these protecting groups is that anytime you add the deprotecting reagent, it is very difficult to prevent your protecting group from also being removed. All right, finally, let's look at the exception to the hemiacetal stability rule, cyclic hemiacetals. If we can make a hemiacetal which is cyclic, it is actually pretty stable. So this will happen in compounds that have both a carbonyl group and an OH group in the same molecule. In the presence of trace amounts of acid or base, these things will cyclize to produce cyclic hemiacetals. Now, just to sort of show you where everything's going, let's add some numbers to this. So I've numbered the atoms 1 through 6 here, starting at the carbonyl group and ending at my oxygen of the alcohol. We can copy the same numbering scheme onto our cyclic compound, and we can see where all the carbons are. So here, hemiacetals, again, are only stable if they're cyclic. Now, the reason why we care about this, the relevance is carbohydrates. So those of you who are going to medical school, dental school, veterinary school, this part's for you. Here, I've shown an acyclic sugar. This is actually glucose, which I've shown in what's known as its open chain form. If you see I've highlighted two groups here, an OH group on the left and the carbonyl group on the right, these two compounds can react to form a stable six-membered ring, cyclic hemiacetal. So these things will equilibrate here between the open chain form and the cyclic form in solution. This is the cyclic form of glucose, also known as glucopyranose. Pyran here, the derivation of this name, a pyran is a common name for a six-membered heterocyclic ether. There's the new bond that we formed. We can see that this compound is a hemiacetal, and in solution, because we can make a cyclic hemiacetal, the cyclic form of glucose is actually the one that is favored at equilibrium.